Okay, so last time I talked about the area interpretation of the integral. Today I want to recap the fundamental theorem of calculus and start to talk about some calculus techniques. So this first video covers material from section 5.3 in the book, and hey, I can't spell the word section. That's great. The fundamental theorem of calculus comes in two different flavors, if you like, or two different versions. I like to think of this as the integral version of the fundamental theorem, and it's the one that we use pretty much every single time we evaluate an integral. So that's pretty fundamental to me. In the wind-up for this theorem, I need to say what I'm talking about and what conditions have to be met. So I need a continuous function f of x, and it has to be continuous on this interval from a to b. And I'm using my square brackets, so this is a closed interval. It contains both of its endpoints. Second, I need another function, which I'll call capital F of x. And capital F of x has the condition that capital F prime of x is equal to f of x. So here is our antiderivative. And we know that there is more than one antiderivative for any given function. The fundamental theorem of calculus says that the value of this definite integral, the integral of f of x dx between a and b, is equal to the difference of capital F evaluated at b minus capital F evaluated at a. I like to think of this as integrals undo derivatives. This lowercase f of x is the derivative of the capital F. And by taking the integral, I am now looking at the capital F function again. So you might have seen a formula like this called displacement, where I'm just looking at the difference of two different function values. And that's another way we can talk about this. I personally find it more useful just to say integrals undo derivatives. Let's take a look at the second form of the fundamental theorem. And this formula comes in the textbook in section 5.4. So just like my other theorem, I need to explain what the players are, what the functions I'm looking at need to satisfy for this theorem to actually be useful. So here again, I have lowercase f of x, and this is a continuous function on the closed interval from a to b. And I'm not going to assign my capital F in the same way. This time, I am building what I'm going to call an area function. Capital F of x is equal to whatever number I get by integrating the lowercase f function between the coordinates a and x, right? So functions are input, output. If you give me some value of x as my input, I will give you some number as the output. So the x is just going to be the upper bound on this integral. And because I'm using my variable x as the end point to the integral, I have to have t as my dummy variable for the actual integration step. The payoff to this version of the theorem is that this capital F of x is one of those antiderivatives for lowercase f of x. So another way to say that is capital F prime is equal to f of x. So this is the version of the fundamental theorem that comes up a little bit less often, but it's still useful. I like to think of this as saying derivatives undo integrals. Right? Here is a function, lowercase f of t. I integrate that up to some coordinate x, and I'm allowing x to change. So that's defining a function. The derivative of my area function is the function that I started out with, lowercase f of x. So that's the other version of the fundamental theorem. Integrals undo derivatives, and derivatives undo integrals.